Okay, welcome to today's lecture, and I thought it'd be cool to fly in today, so we're going to fly in L12a, lecture 12a, so there'll be a B as well. Bernoulli Equation and Stagnation. Okay, actually added the name Stagnation to emphasize it. I think because in past semesters when I've taught this, people get out of this course and stagnation just kind of gets lost. Okay, so this is really cool because we are finally getting into what I consider in some ways like the real fluid mechanics. Like continuity really is the beginning of it. But we're going to start talking about Bernoulli. And Bernoulli is one of the most powerful equations. We've kind of already gotten a very simplified version of it, which was the kind of the hydrostatic law, but that was for fluid that does not move, hence the name hydrostatic. So what we're going to do here is to understand the assumptions, we're going to derive Bernoulli. Then we're going to start applying it in a lot of different ways, and out of the applications, stagnation will come. Okay, so this first part, A, is almost certainly will probably be entirely taken up by a derivation. So as with all derivations in my course, pay attention, watch it. You don't need to copy it all down, but it's good to understand what is going on and why it's there, in case in the future you need to derive your own version of Bernoulli or something similar. You can kind of follow the steps. So what we're going to do is we're going to do a derivation along a streamline. So we now know what streamlines are. Okay, so there's no flow perpendicular to this line. So we're going to look at a stream tube. So there's a tube of fluid that is moving along this stream here. Okay, and the front of it and the back of it both have a cross-sectional area of A. Okay, and it is flowing in this direction. Okay, that direction, which is the streamwise direction. Okay, so normally you have X and you have Y, or Z. So in this case, we do have X and we do have Z. And Z is definitely up in this case. Okay, we're not going to use Y. Some programs will use Y, but a lot of textbooks use Z, and that's the way that I was taught, and so that's the way we're going to use this. And so this triangle right here, you can't even see the triangle yet, but here's a triangle. Okay, with this distance from here to here, well, that's delta S. This is going to be delta X, and this one right here is going to be delta Z. Okay, and that's important that you understand that, because that is going to play into some of the things that we're going to do. I want to note, because it is going to be useful for us. So as an aside, I can say, well, the sine of let's say this angle right here, theta. Okay, that's the opposite, which is going to be delta Z over the hypotenuse, which is delta S. Okay, because that's definitely going to play a role. So we're gonna use that later. So we're just gonna kind of put that off to the side. Okay, what else do we want to know? Well, what we're gonna do on this is we are going to, I guess I'll do this in a slightly different color. We'll do this in blue. I want to think about the forces on this little stream tube as it's moving along. So the first thing that we must note is that we have pressures. So on the back of this thing, I've got the pressure on the back times the area on the back. Okay? On the front, okay, now notice pressure is always pushing, it can't pull. So this pressure is going to be P plus delta P, okay, times that area. Now you might say, well, how do I know that the pressure went up? I don't know. The pressure could have gone down. But I've got a delta P there. The delta P could be positive or negative. All I'm saying is it's kind of like the pressure on the back. It's just different by some amount, okay? And then what other forces do we have? Okay, think about this. What other forces do we have on this sucker? Okay, so remember, when we're looking for forces, we have to think about body forces. Oh, there's a body force. What's the body force? Oh, it's weight. Okay, so the weight is going like this. That's the weight. What other forces do we have? Anybody? Okay, so there are surface forces. So basically these pressures are surface forces. There is one other surface force, and that would be if the fluid is moving from down here to up here, there would be a viscosity. Okay, and I'm going to draw this in a different color. I'm going to draw it red. So the viscosity would, well, it might be working to slow it down. It depends on what the fluid on either side of this is doing. So it could be speeding it up if the fluid around it is moving faster. And but I'm going to draw it as if it's slowing it down. But here's why I'm drawing it in red. So we're going to assume no viscosity. Okay? And this assumption is often called that it is inviscid flow. Inviscid means no viscosity. Okay. I'm also going to say, I can also, along with this, say no pumps or turbines, or there's really no other forces on this. Okay. So the only forces on this flow are the weight and the pressure. Okay. So what we're going to do now that I've done that, okay, so we're not going to include those, okay, in our analysis. Okay. So there will be a time when we will start to deal with those things, but the time is not now. Okay, we're going to build this kind of slowly. Okay, and the Bernoulli is the second step after the hydrostatic assumption, and then we're going to go into energy equation, and then we're going to make the energy equation very complicated, and you're going to wish for the days of good old Bernoulli. So what we're going to do here now is I want to think about sum of the forces in the s direction equals mass times acceleration in the s direction. Okay, which is kind of nice because the beautiful thing about this derivation is that it just uses first principles. Okay, so well, we've got the force on the back, PA. Okay, we've got the force on the front, minus P plus delta P times that same area. Okay, and then we've got the weight, okay, minus the weight. But the weight, unfortunately, is a little bit more difficult, isn't it? Yeah, the weight kind of stinks, right? Because it's at an angle. Okay, so I guess the portion of the weight that we're concerned with is this portion right here. Okay, we don't care about this portion here. Okay, so how do we get at that? Well, let's see. Okay, so what we're going to do is we're going to recognize that this angle right here, along with the original theta, all add up to 180. Okay, because this is a right triangle right here, which means that this angle right here adds up to this angle and this right angle. So to make 180, so this angle has to be theta. Okay, so that means the portion that's going in the portion right here, well, that's W times, that's the opposite, so W sine theta. Okay, so we'll make this W sine theta, okay, equals, now we need the mass. Okay, how do we get the mass? Well, that's going to be, we'll just call it the mass for now, and the acceleration in the S direction. All right, so hopefully, this one's fine, with the one tricky thing being getting that angle. Play with it and make sure you can get that angle. Okay, so I'm going to just recopy this line for the most part. Hopefully you should be seeing that those PAs are going to go away. And how do we do the weight in fluids class? So weight in fluids class is usually gamma times the volume. So we'll do gamma, and in this case the volume is, well, it's kind of hard to see at this point, but it's going to be this area on the front times the length of this thing. So it's area times delta S. So area times delta S, okay, sine theta equals the mass. Well, the mass, similarly in fluids class, is rho times the volume, same volume, A times delta S times A sub S. Okay, let's see, what else do we want to do? Oh, well, the last thing we want to do here, I'm just going to go ahead and erase it, is I'm going to replace this sine of theta with this thing right here. Okay, so I'm going to get delta Z over delta S. Okay, and hopefully you can see why I wanted to do that. Okay, so working downwards, this thing becomes negative delta P times the area. Well, maybe we'll make it area up front because that looks a little bit prettier. Minus gamma area, and the delta S's cancel. I'm left with delta Z equals rho times area times delta S times AS. Okay, noticing that all those areas are going to cancel because every term has one. Okay, so I'm left with negative delta P minus gamma delta Z equals rho delta S. Okay, AS. Okay. So what we want to do now is I want to divide everything by delta S. Okay, and what we're going to it if this thing will allow me to scroll, which it sometimes doesn't want to do. Okay, so at this point we're just doing some algebra here. Delta P delta S minus gamma delta Z delta S. Okay, notice those are looking a lot like derivatives. Equals rho AS. Okay, this thing, okay, if I, what I'm going to do is I'm going to take the limit of this as delta S goes to 0, because I want this in derivative form. Okay, and I'm going to get negative dp ds minus gamma dz ds equals rho AS. Okay, and now we're going to make our second assumption. I'm going to put it in red because what I want to do is I want to bring this rho inside there. So in order to do that, I'm going to assume that, not rho, gamma. I'm going to assume that gamma is constant. Okay, so what that allows me to do is that allows me to write this as negative d by ds of pressure plus gamma z equals rho AS. Okay, this equation has a special name. This is the Eulers equation. And there's quite a few forms of this equation. And what it says, so this thing right here, this is the piezometric head. Piezometric head. Okay, and you may remember, I don't really want to do that in red because that's not a assumption. Anyway, let's imagine this in blue. And you may remember, we went back to when we did hydrostatic, okay? In a hydrostatic situation, you may remember, okay, recall for hydrostatic fluid, that, let's see here, P plus gamma Z equals a constant. Okay, you may recall that. Okay, so this is the piezometric head. In this case, though, we're not hydrostatic. We've got movement. Okay, we've got acceleration. Okay, so that's the next thing we're going to deal with. Okay, so this is the Eulers equation. Make note of it. It's an intermediate step. We probably won't use it very often. This term piezometric head is one that will show up from time to time. So make sure to make note of it because it's going to show up. Okay, so what we want to do now is we're gonna expand out this acceleration in the s direction. Okay, so we're gonna say, okay, negative d by ds of the piezometric head equals rho, okay, the density, times dv dt plus v dv ds. Okay, noticing that in this case we only have one direction because there's when I wrote this large acceleration terms out here, there were a few more terms, but in this case there's no flow across the streamline, so I only have one direction for acceleration to happen. I should note also, by the way, that this is really just, we started with, up here we started with Newton's second law and we're still there, right? These are the sum of forces. This is the acceleration. Okay, it's just uglier now. Okay, it doesn't mean that that's not what it is. Okay, so one thing I want to do here is I want to make another assumption here in order to go to the next step. So I'm going to, well, let's do it right here. I'm going to assume steady flow. Steady flow. Okay, by doing that, I can get rid of this portion right here because there is no velocity, there's no dv dt. Okay, so now we are left with something pretty simple, or maybe not that simple, d by ds of the pressure plus gamma z equals, okay, rho, and I'm not going to write this bit because there's going to be a little trick here, and I remember this trick always confused me the most. So what I want to do is I want to harken back to your calculus days because this trick always gave me the fits. Okay, so let's suppose we had v squared, and I wanted to take the derivative of it with respect to s in this case. Okay, what would the derivative of that be? Well, it would be d, that's not a d. It would be dv. That's terrible. I've done it twice in a row. Okay, it would be 2v, right? So 2v, so you bring the 2 down like that, right? And then the 2 would become a 1. And then you'd have the chain rule, dv ds. Okay, so note that I could say that 1/2 dv squared ds equals v dv ds. Okay, if I divide this side by 2 and this side by 2. Okay, so that's what I'm going to do right here. Is basically I'm going to replace v dv ds right here with 1/2 dv squared ds. 1/2 dv squared ds. That step always threw me for a loop whenever I saw this derivation. So I wanted to kind of take a moment and make sure you understand that and where it comes from. Okay, so we're here, and these derivatives are now, everything's with respect to s, so these all become ordinary differential equations. This becomes just a d, and that becomes a d. This becomes a d, and this becomes a d. All right, so now we've got ordinary derivatives, and this starts to become kind of cool, right? So watch, we are now going to we're going to kind of start bringing all this stuff together. We note that because we've already assumed that everything is, we already made this incompressible fluid up here. So that means this rho can go inside that derivative. This 1/2 can go inside that derivative. So that means algebraically I can write d by ds of p plus gamma z, let's see here, plus rho v squared on 2 equals 0. So I brought everything over to the left-hand side, and I'm left with this. Pressure plus gamma z equals rho v squared on 2, okay, equals 0. So one way to say that, or a better way to say that, is that I can say that p plus gamma z plus rho v squared on 2 equals a constant, okay, along a streamline. That's what that d by ds means. Okay, so in the streamline's direction, along a streamline, we can say that this quantity is a constant. Okay, another way, and more typically, what happens is we kind of divide this whole thing by gamma. So we end up with p on gamma plus z plus v squared. Now remember, gamma is rho g, so it just gives me 2g on the bottom here equals a constant. Obviously, that's a different constant, but it's not really important. Okay, so we can again say along a streamline. Okay, and so this is the way that we will commonly use this, or one of the common ways we will use this. And before I continue with this, I want to think about these two things. This is the potential energy. Potential energy. Okay, this is the potential energy stored due to pressure. This is the potential energy stored due to elevation. And this right here is the kinetic energy. Okay, so, typically you think of kinetic energy as mass times velocity squared. Well, that's what this was right here. Or usually, I think it's usually 1/2 mass times velocity squared. So that's what this is. Instead of mass, we've got rho. Okay, so it's kinetic energy per unit volume. Anyway, so we've kind of got this split up into these three different types of energy. And I will note that this is pressure head. This is what we call pressure head. Okay, this is elevation head. And this will be called velocity head. Okay, these are called heads. Okay, they just call it head. I have no earthly idea why they call it head. All of these are measured in units of length. Okay, and there's a very good reason for that. So up here, they're all measured in units of pressures. Okay, but here, they're all measured in lengths. Okay, measured in units of length. Okay, and there's a very good reason for that, and we're going to get to that eventually. But typically, so I'm going to write this out. So instead of calling that constant, usually the way we're going to use this equation over and over and over and over and over again, z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G, okay, where 1 and 2 are on streamline. Okay, that's, I guess that's assumption number 1. Assumption number 2, let's see what other assumptions did we make. Go up here, steady flow. Okay, steady flow. What other assumptions did we make? Okay, gamma is constant. Gamma is constant. So if gamma is constant, we're dealing with incompressible flow. So 3. Incompressible flow. Incompressible. I guess fluid, really. Okay, what else do we have? I think there was a 4th one. Let's go see what we got. Okay, no viscosity or no pumps or turbines. Okay, so no energy added or lost due to, okay, so inviscid flow. Okay, so that means no viscosity. And then I could also say slash no pumps or turbines, no mechanical energy added. Okay, that's basically along that streamline. Okay, and I think that that's pretty much it. Let's see here, steady and viscid, incompressible along a streamline. And yeah. So remembering, of course, that incompressible means that rho and gamma are constant. Okay. So this is the Bernoulli equation. Okay. And this is what this is all about right here. Okay, we're going to use this so much you're going to memorize it and you're not even going to try. Okay, this is the Bernoulli equation. Okay, you're going to actually end up liking this one because this will be like the simple version of the energy equation. All right, so that's it, and we're going to move on to part B.